Hi, Flash Hour is my name. When I'm not making wedges of cash in the city, I'm blatting around on my bike. It's fast, mean and expensive, not unlike myself. It'll go 0 to 60 before you can say bye, 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 sell, 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 and it's got more horsepower than the Grand National. You see, it's a dog-eat-dog world out there. I'm talking speed, acceleration, forces, and motion. Hello, Jones is my name, and chauffeuring Mrs. Gideon around is my game. And, of course, cricket. Yes. Well, it's all a matter of distance over time, isn't it? Yes, I've got the time, so you better keep your distance. Oh, no, only joking. What I'm really talking about, of course, is speed and how to determine it. Yes, and you won't go far wrong if you always remember that speed is distance over time.
Speed equals distance over time. So if you cover 50 kilometres in half an hour, your speed will be 100 kilometres per hour. A graph helps to calculate your speed. Distance on the vertical axis and time on the horizontal axis.
Starting off, I begin to cover a greater amount of distance in a shorter amount of time. This can be shown as an upwards curve on a graph. That is because my speed is increasing. Eventually, I reach a constant cruising speed, which is never over 50 kilometres an hour. No, never, never over 50. Unless, of course, when it's over 60. Oh, only joking. You can always tell, of course, when you've reached a constant speed, because the curve is a straight line. Yes, and you must always keep a very good lookout, in case anything untoward should happen. Yeah. Good grief, what do you know? This calls for an emergency stop! Sorry about that, old chap. Oh, dear, almost caught that little critter. Lady Gideon would never have forgiven me, yes. She's a founder member of the RSPCA, the Royal Society for the Prevention of Cruelty to Aristocrats. Ha-ha! Only joking, of course. Right then, the wonderful thing about making a graph of your journey is, here's my graph, is that at any point along this curve, you can work out your speed. You see, this is the point where I started off. Here's nothing there. I gradually gained speed, and this straight line is my constant speed. Then I slowed up because that little critter jumped down in front of me. Look, there you are. He's squashed on that line there. Or not, as the case may be. Right, what if, for example, I wanted to work out my constant speed? Well, that's this straight line here. All I do is I draw a line from the beginning down to the time axis. There you are. That's the beginning of my constant speed. And then my constant speed ends around about there. There you are. I'll draw another line down. Smashing. And that gives me my time during my constant speed, which is 50 minus 20. That's 30 seconds, which, of course, is half a minute, if you're clever. If I want to find out for how far I travelled at a constant speed, I draw another line across here. There we are. Goes to 200. And another line, I trace it across. There we are, reach 700. There we go. Right, so in order to find out the distance I travelled at my constant speed, it's 700 minus 200, which, of course, is 500. And that time there was 30 seconds. That's half a minute. Now, 500 metres is, of course, half a kilometre. 30 seconds is half a minute.
Speed equals distance over time. So that's 500 metres divided by 30 seconds, which is 16.7 metres per second.
So what's that? That's 60 kilometres an hour. Well, we can't all be perfect, can we? Anyway, yes, when that little critter ran out, of course, I slammed on the anchors, slammed them on, and there we are. I slowed to a halt, but of course the time was still ticking. So my line carries on, but I'm not moving, so it's flat. A little bit like I'll be when Mrs. getting clapped around the head for being late. And with that in mind, I'd like to bid you farewell. Ta-ra, toodle pip, and thank you. Ta-ra. Just listen to that. Sorted, sweet as a nut. Now then, big shout going out to the Forces and Motion posse in the house. If you're in the house, make some noise. Just me then. All right, well, that geezer in the Rolls Royce, right? It was well sorted for time and distance. But from where I'm coming from, it's acceleration that impresses your mates. Oh, yes. And the better you can understand it and illustrate it, the more impressed they'll be. Now then, this extremely pucker motor in a couple of seconds' time will be accelerating because I'll be putting my foot down on the juice pedal. See you later. Now then, this racing track is wicked to demonstrate what on earth I'm talking about and put my sweet as a nut motor through its paces. Now we know that speed equals distance over time, so all I've got to do to get my speed is measure my time between the distance markers I've located at the side of the track, over there. You'll see them as I blast past.
If we measure the slope at different points along the graph, we get Andy's speed at those points. If, for example, we want to find out Andy's speed after he's been travelling for 8 seconds, we can simply draw a straight line to the graph at 8 seconds and calculate its slope or gradient. To calculate the gradient, we need to divide the distance by the time. In this case, the distance is 200 metres minus 60 metres, which is 140 metres. Similarly, if we extend the line to the time axis, the time is 11.8 seconds minus 5.8 seconds, which equals 6 seconds. The gradient is therefore 140 metres divided by 6 seconds, which is 23.3 metres per second, and that's 84 kilometres per hour. To get Andy's speed at any other time, we can calculate the gradient at these points in exactly the same way, and we end up with a table of speed against time.
Now this is where the clever bit comes in.
If we plot these points on a speed-time graph, speed on the vertical axis and time on the horizontal axis, we can work out acceleration by measuring the gradient of the speed-time graph at any point.
In the manual, it says that my kicking motor does 0 to 90 in 9 seconds. But as you can see, I've souped it up and it does it in 8.5. Nice one. Equally crucial is the ability to show the stopping distances of your motor, which will be serious considering the amount of money I've spent on my tyres. Stopping distance is calculated with your distance time setup. So, if I slam on the anchors at 40 kilometres an hour, let's see what happens.
The measuring wheel is used to determine the distance travelled in each case. Although the time taken to stop doesn't change very much, the distance travelled increases dramatically. At 40 kilometres per hour, the car travels 9.8 metres and comes to a stop in 2 seconds. At 80 kilometres per hour, the car travels 25.1 metres and comes to a stop in 2.7 seconds.
And when you know your stopping distances, write them down and post them through the letterboxes of everyone's house in the neighbourhood. Then they all know who's got the fattest tyres in the place. Wicked. OK, baby, ciao. Now it's time to see what real acceleration and deceleration are all about. And just in case you think I'm cheating, here's the Speedo captured live on camera. Read it and weep. As you can see, the graph's gone completely off the scale. I'm doing about 230 kilometres per hour, and that's legal, at least on a racetrack. The mass of a motorbike compared to a car is much less, and this means that the bike gets started much more quickly. This shows in its acceleration. Of course, the fact that I have a fantastic engine hidden in there also has got a lot to do with it. And apart from smashing the opposition when it comes to acceleration, emergency stops at the same speeds as an equivalent car will also prove the bike to be much more efficient. So remember, speed equals distance over time, and you get that from your distance time graph. And time equals money, so I'm out of here. Acceleration is wicked, and you work it out from your speed time graph. Plus, there's an awesome night happening this Thursday at Club Crucial. Give us a nod, and I'll put your name on the door. And remember, if you're planning on making an emergency stop, the faster you're going, the longer distance you'll travel. Oh, and it ain't what you do, it's the way that you do it. Yes. Toodle pip.
Unbelievable stuff. Now that surely has got to be as wild as it gets. Pah! My dream is to fly through the sky, not just to fall, but to actually fly. And maybe even one day, maybe we could actually land without a parachute. Let's see what the laws of physics have to say about that. Now, if we're going to demonstrate the physics of falling, first we need someone who's prepared to fall. Second, we need some very technical people who are going to... What are you going to do? Are they going to make some measurements? And thirdly, we need a stopwatch, which is in the camera. I said first we need someone who's prepared to fall. I see, that's me. Now this is a deadly serious science experiment. We're not here to have fun. Let's see how fast we can go.
How fast was that?
We put several markers on the crane. They're at 10-metre intervals all throughout the crane, so we can help us gauge exactly how low Adrian comes with his jump and how much he returns to. On top of which, we'd actually worked out on a calculator exactly, bearing in mind his weight and the stretch of the rope, the same thing, how much he stretches to and how much he returns to.
On the first descent, Adrian takes 4.4 seconds to fall 63 metres. On the second descent, he takes 4.7 seconds to fall 40 metres. And finally, on the third descent, he takes 4.3 seconds to fall 35 metres. Using the formula speed equals distance over time, his average speed on the first descent is 14.3 metres per second. The average speed on the second descent is 8.5 metres per second. Finally, his average speed on the third descent is 8.1 metres per second. So Adrian's average speed depends on the height of his fall. As he falls, he starts to accelerate. So the shorter his fall, the less his top speed. The calculated speed for each descent is the average of his initial speed, which is 0 at the start of the jump, and his top speed. This decreases with each descent.
So the first conclusion is, the higher you jump from, the higher your top speed's going to be, which means I can jump from here without a parachute. It's not very fast, though, is it? Now, if we want to jump off something very, very high, something extremely tall, and live, we have to find a way to slow ourselves down. So this time, I'm going to jump like a base jumper, like a flying squirrel. Wearing this big suit, I'm going to try and catch all the air I can. Ready, steady, go!
By wearing his suit and jumping like a flying squirrel, Adrian is increasing the air resistance on his body. Air resistance depends on shape.
As I was coming off the top, I didn't get the rush of air coming past me quite as much. It felt much slower. Let's see what our technical experts think of that.
On the first descent, Adrian takes 5 seconds to fall 63 metres. On the second descent, he takes 4.8 seconds to fall 35 metres. And finally, on the third descent, he takes 4.2 seconds to fall 30 metres. Again, using speed equals distance over time, his average speed on the first descent is 12.6 metres per second. His average speed on the second descent is 7.3 metres per second. And finally, his average speed on the third descent is 7.1 metres per second. So, his squirrel jump is slower than his normal first jump. The average speed on his normal jump was 14.3 metres per second. The average speed for his squirrel jump is only 12.6 metres per second.
Right.
Upside down. Do it upside down. Now, the second conclusion is that I can slow myself down while I'm falling by changing the shape of my body. So how fast can we go? When we skydive from an aeroplane at about 4,500 meters, we accelerate, and we accelerate, and we accelerate. But do we continue to just go faster and faster? There's a speed you reach, and you just can go no faster. That's terminal velocity. For a skydiver flying flat like this on his belly, that's about 120-something miles an hour. But we want to go faster than that. If we can clean up the shape, if we can make ourselves more aerodynamic, like a big flying wing, like a sort of a human jet fighter, we can go faster. We can go faster than 200 miles an hour. We can go faster than 300 miles an hour. We can average 340 miles an hour just from 4,500 meters. That's my terminal velocity.
It's time to play Spaceball. The ball accelerates until it reaches its terminal or maximum velocity. But Adrian soon catches up with it, meaning that his terminal velocity is faster. But that's not the end of the story. The only way to play Spaceball is by being able to alter your terminal velocity. Sometimes Adrian and his friends fall faster than the ball, and sometimes they fall slower. The ball can't change its terminal velocity because it can't change shape, but humans can change their terminal velocity by changing their body shape. A leg bend, or an outstretched arm, can increase or decrease the air resistance on the body. This allows them to fall slower or faster than the ball. But terminal velocities well in excess of 100 miles per hour are definitely too fast for a safe landing. So, until Adrian perfects the art of flying, he will have to rely on his parachute to slow him down. Parachutes dramatically increase air resistance, creating a big upward force to slow him down for a safe landing.